guys. Tonight we drift farther into the future than the human mind was ever really designed to handle. You float above the Earth as city lights flicker beneath clouds, satellites quietly glide overhead, and the stars seem fixed and eternal, like they've always been there and always will be. But they won't. Every glowing thing in the sky, every galaxy, every atom inside your body is moving toward an ending so vast and so slow that your brain almost refuses to picture it. Which is fair. Honestly, your ancestors struggled to remember where they left their sandals, and now you're trying to imagine the death of space-time itself. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're settling in tonight, post your location and local time down below. It's strangely comforting knowing people all around the world are listening together while the universe quietly races toward oblivion. Now, dim the lights. Maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You begin in the present universe, where the night sky still feels alive. The Milky Way stretches overhead like powdered frost across black glass. Stars are born inside enormous clouds of gas. Galaxies collide in slow-motion dances lasting billions of years. Black holes lurk quietly in the centers of galaxies like cosmic landlords collecting invisible rent. For most of human history, people assumed the heavens were permanent. Ancient Greek philosophers believed the stars existed in perfect, unchanging spheres. Medieval astronomers imagined the universe as eternal and fixed. Even Isaac Newton privately worried that gravity should eventually pull all stars together, though he tried not to dwell on it too much, probably because having a universe-ending existential crisis in the 1600s sounds exhausting enough without modern coffee. Then came the 20th century, when astronomers discovered something deeply unsettling. The universe was expanding. Galaxies were moving away from one another in every direction. Edwin Hubble observed this in the 1920s, fundamentally changing humanity's understanding of reality forever. At first, that expansion sounded harmless. Space getting bigger, fine. Very polite, very respectful. But then scientists realized something stranger. The expansion was accelerating. Galaxies weren't merely drifting apart. They were speeding away faster and faster, pushed by something mysterious we now call dark energy. And that discovery transformed the universe from a stable home into something temporary. You drift outward from Earth now, passing Mars, Jupiter, the icy outer planets, until the sun itself becomes only another bright star among trillions. The galaxy around you hums with activity. Nebulae glow pink and blue. Pulsars spin like broken cosmic lighthouses. Somewhere, stars explode in supernovas powerful enough to outshine entire galaxies. But even now, the universe is aging. That part always feels strange. You normally think of aging as wrinkles, grey hair, mysterious knee when standing up too fast. But the cosmos ages too. Stars consume hydrogen fuel inside their cores. Galaxies slowly use up the gas needed to create new stars. Every brilliant object in existence survives by burning finite reserves. Entropy quietly rules everything. That word sounds like the name of a villain from a low-budget sci-fi movie, but it's actually one of the most important concepts in physics. Entropy measures disorder, and according to the second law of thermodynamics, entropy in the universe tends to increase over time. In simpler terms, ordered systems naturally fall apart. Hot coffee cools down, buildings decay, batteries die. Leftover pizza becomes biologically questionable after enough hours. The universe itself follows the same rule. Historians still argue whether ancient civilizations truly grasped cyclical cosmic destruction or merely used it symbolically in mythology. Hindu cosmology described repeating cosmic cycles thousands of years before modern astrophysics emerged. Norse mythology imagined Ragnarok, the destruction and rebirth of the world. Even ancient Mayan traditions described eras of creation ending catastrophically. Humans have always sensed, in some deep instinctive way, That permanence is an illusion. You continue drifting through the Milky Way, and everywhere you look, gravity shapes matter into temporary beauty. Spiral arms curl elegantly around the galactic center. Young blue stars blaze with furious brightness, but blue stars live fast and die young. Massive stars burn through fuel quickly, surviving only millions of years instead of billions. Ironically, the small, dim red dwarf stars are the true survivors of the cosmos. They burn so slowly they may last trillions of years. Tiny, quiet, efficient. The cosmic equivalent of somebody still using a 2009 laptop while everyone else's fancy technology catches fire. And yet even they will eventually fade. The future ahead unfolds across timescales so enormous they barely fit into language. Millions of years, billions, trillions. Numbers so huge they stop feeling meaningful, and instead become soft abstract fog inside the mind. You pass beyond the Milky Way now, watching other galaxies drift away through expanding space. Right now, the Andromeda Galaxy is moving toward us and will collide with the Milky Way in roughly 4.5 billion years. That collision sounds dramatic, but galaxies are mostly empty space. Stars rarely crash directly into one another. Instead, the galaxies will slowly merge into one giant elliptical galaxy over millions of years, a cosmic traffic accident happening in extreme slow motion. Meanwhile, farther galaxies vanish from view entirely. Their light stretches as space expands, becoming redder and weaker. Eventually, distant galaxies will move away faster than light can bridge the growing gap between them. Future civilizations may look into the night sky and see only darkness beyond their local galactic neighborhood. Imagine that loneliness. Astronomers in the distant future might never know other galaxies existed at all. The evidence for the Big Bang itself could disappear beyond the cosmic horizon. Entire chapters of cosmic history erased simply because the universe expanded too much. There's something oddly melancholy about that. Not violent, not explosive, just quiet forgetting. You continue floating deeper into time, and the stars around you already seem slightly fewer than before. The universe still glows, still lives, still moves with magnificent complexity. But underneath everything, entropy patiently waits like an ocean tide, and the tide never stops rising. The stars around you continue burning, but something feels subtly different now. The universe has entered middle age. Not old yet, not dying yet, but no longer young and reckless either. The bright chaos of cosmic youth is fading into something quieter, slower, more tired. You drift past enormous stellar nurseries where stars are still being born inside cold clouds of hydrogen gas. Pillars of glowing dust stretch for light years like illuminated mountains floating in darkness. New suns ignite here constantly, flooding nearby space with heat and radiation. If you stare long enough, the entire galaxy almost feels immortal, but appearances, as usual, are wildly misleading. Star formation across the universe has already slowed dramatically compared to billions of years ago. Astronomers estimate the peak era of star birth happened roughly 10 billion years in the past, during what some scientists casually call cosmic noon. Back then, galaxies produced stars at furious rates. The universe was basically running on astronomical caffeine. Now things are calmer. You move through the Milky Way and notice large regions where the raw gas needed for new stars has already been exhausted. Ancient generations of stars fused hydrogen into heavier elements, then exploded and scattered those materials across space. Every atom of oxygen in your lungs, every bit of calcium in your bones, every trace of iron in your blood was forged inside long-dead stars. Carl Sagan famously said, "You are made of star stuff," which sounds poetic until you remember that stars usually explode violently before donating their materials. Very generous, slightly aggressive. You pass near a red giant star now, swollen to enormous size near the end of its life. Its outer layers pulse slowly outward, glowing deep orange against black space. In around 5 billion years, your own sun will become one of these giants. It will expand so dramatically, the that Mercury and Venus will almost certainly disappear inside it. Historians still argue whether Earth itself would survive briefly as a scorched rock or vanish completely beneath the Sun's outer atmosphere. Either option feels fairly inconvenient. Long before that happens, though, Earth will already become nearly uninhabitable. The Sun gradually grows brighter over time. In roughly 1 billion years, increasing solar heat may boil away Earth's oceans entirely. The planet that once held forests, whales, cities, arguments on the internet about pineapple pizza, all of it reduced to a dry, burning wasteland orbiting an aging star. You continue drifting farther into the future. The night sky slowly changes around you. Massive blue stars disappear first because they burn fuel incredibly quickly. Those brilliant giants live only millions of years before exploding as supernovas. Smaller stars survive longer. Yellow stars like the Sun endure billions of years. Tiny red dwarfs may survive trillions, and red dwarfs become increasingly important now. These dim little stars are almost comically efficient. They sip hydrogen slowly and steadily, glowing faintly for unimaginable spans of time. Some astronomers believe no red dwarf has even died naturally yet, because the universe itself is still too young. Imagine lasting so long that reality hasn't existed long enough to watch your full life cycle. That's cosmic patience right there. Around many of these red dwarfs, planets still orbit quietly. Perhaps some hold civilizations. Perhaps strange future beings evolve beneath dark crimson skies, where daylight feels more like permanent sunset. Fringe theories even suggest advanced civilizations might deliberately migrate toward red dwarf systems to maximize survival time in the far future, which honestly sounds like humanity moving into the universe's cheapest long-term rental housing. You drift outward beyond local galaxies now. The cosmic expansion has become impossible to ignore. Galaxies move farther apart every moment. Space itself stretches continuously, carrying entire clusters of stars away into unreachable distance. This expansion was first observed through redshift. Light from distant galaxies becomes stretched into longer wavelengths as those galaxies recede. Edwin Hubble's observations changed cosmology forever by proving the universe was dynamic rather than static. Then came the deeper shock. In the late 1990s, astronomers studying distant supernovas discovered expansion wasn't slowing down from gravity as expected. Instead, it was accelerating. Something mysterious pushed the cosmos apart faster over time. Scientists named this invisible force dark energy, though that name mostly translates to, "We genuinely have no idea what this is." Dark energy now appears to make up roughly 70% of the universe's total energy content. Ordinary matter, including stars, planets, people, cats, sandwiches, and every embarrassing thing humanity has ever posted online, forms only a tiny fraction of reality. You continue through deep time, while galaxies gradually vanish beyond the observable horizon. At first, they merely grow dimmer, then redder. Eventually, their light stretches beyond detectability entirely. One by one, the distant galaxies disappear. Future astronomers may live in isolated galactic islands surrounded by total darkness, unable to see evidence of the wider cosmos at all. They might conclude the entire universe contains only their local stars. The Big Bang itself could become scientifically unknowable because the evidence will have expanded beyond observation. That idea unsettles many physicists. Knowledge itself has an expiration date. You float beside the future merged remains of the Milky Way and Andromeda galaxies now. Their collision has long since completed, forming one massive elliptical galaxy, sometimes nicknamed Milkomeda. The elegant spiral arms are gone. Star formation slows dramatically. Ancient white dwarf stars drift through the dark like cooling embers. A quirky astronomical tidbit from the 20th century claimed the universe might eventually end in something called proton decay, where even stable matter slowly falls apart. Scientists still debate whether protons truly decay at all. If they do, The timescales involved are absurd beyond comprehension, potentially lasting over 10 cubic years. That number barely even feels real. It looks less like mathematics and more like somebody fell asleep on a keyboard. Meanwhile, entropy continues increasing patiently everywhere. Black holes consume wandering stars. Dead stellar remnants accumulate. The cosmos grows dimmer century by century, millennium by millennium, eon by eon. Yet the process feels strangely calm. No sudden catastrophe, no giant explosion, just gradual exhaustion, like a campfire quietly burning down after everyone has gone to sleep. You drift farther still, and the once crowded heavens already look emptier than before. The universe has not died yet, far from it, but for the first time, you can truly sense the direction everything is moving. Toward darkness, toward silence, toward a future where even the stars themselves finally run out of breath. The universe grows quieter now, not suddenly, not dramatically. There's no cosmic alarm bell echoing through space, no giant sign flashing closing soon. Instead, the change creeps in so slowly that entire civilizations could rise, vanish, and turn to myth before noticing the stars thinning overhead. You drift through the future remains of galaxies that once blazed with blue young stars. Now most of those brilliant suns are gone. Supernovas have become increasingly rare. The great stellar nurseries that once glowed with newborn light are mostly dark clouds drifting unused through space. The age of easy star formation is ending. You pass clusters of ancient white dwarf stars, small dense remnants left behind after ordinary stars exhaust their fuel. These stellar corpses no longer produce energy through fusion. They simply radiate leftover heat into the darkness, cooling endlessly like forgotten coals after a fire. Some future astronomers once nicknamed this upcoming era the degenerate age, which sounds less like astrophysics and more like a deeply concerning casino in Las Vegas. Still, the name stuck. You continue deeper into time, and the universe feels emptier with every passing million years. Entire galaxies disappear beyond the expanding cosmic horizon. Space itself stretches so aggressively that distant light can never reach you again. This isolation becomes one of the strangest consequences of dark energy. Right now, if you stand beneath a clear night sky on Earth, you can still see neighboring galaxies through telescopes. The Andromeda galaxy alone contains roughly 1 trillion stars. But in the unimaginably distant future, nearly all galaxies outside your local gravitational group will vanish permanently from view. Future civilizations may grow up under empty skies, unaware the wider universe ever existed. Imagine living in a cosmic village after the roads to every other city have been erased. Historians still argue whether humanity psychologically depends on the idea of an infinite visible cosmos. Some scholars believe losing the stars would deeply affect intelligent civilizations emotionally and spiritually. Others argue beings born into dark, isolated skies would simply consider emptiness normal. Either way, it feels lonely. You drift toward the future Milky galaxy, the enormous merged remnant of the Milky Way and Andromeda. By now, the collision between the two galaxies has long finished. The elegant spiral structure disappeared ages ago, replaced by a swollen elliptical cloud of aging stars. The night sky inside this future galaxy looks very different. Fewer bright young stars, more dim red dwarfs, vast regions of darkness between ancient stellar remnants. And the red dwarfs continue surviving. These tiny stars dominate the later universe because they burn fuel with extraordinary patience. Some may survive for up to 10 trillion years. Their light glows faint red, casting perpetual twilight across any surviving planets. If civilizations still exist around such stars, their concept of time may become almost incomprehensible compared to modern humanity. Empires could endure longer than entire geological eras on present-day Earth. Languages might evolve beyond recognition thousands of times over. And yet even those stars eventually die. You pass one now nearing the end of its impossibly long lifespan. It dims gradually over billions upon billions of years until fusion finally stops altogether. No explosion, no grand finale, just fading. That's one of the universe's favorite endings, honestly. Quiet disappointment. Nearby, dead neutron stars drift invisibly through space. These ultra-dense remnants formed long ago when massive stars collapsed under gravity. A teaspoon of neutron star material would weigh billions of tons on Earth, which means carrying one in your pocket would ruin your pants immediately. Black holes have also become increasingly common. You begin noticing them everywhere now. Some formed from collapsing stars. Others grew supermassive inside galactic centers over trillions of years. Without many bright new stars left, black holes increasingly dominate the architecture of the cosmos. Stars occasionally wander too close and get torn apart by tidal forces, stretched into glowing streams of gas spiraling inward. Astronomers call these tidal disruption events. The black hole feeds briefly, releasing enormous radiation before falling quiet again, like the universe absent-mindedly snacking in the dark. Meanwhile, entropy keeps climbing. That relentless increase matters more than anything else in cosmic history. Entropy doesn't merely describe messiness. It defines the direction of time itself. A shattered glass can scatter across the floor naturally, but scattered shards never spontaneously leap upward into a perfect drinking glass again. The universe remembers forward, never backward. This gradual slide toward disorder affects everything. Stars use up fuel, heat spreads evenly, useful energy disappears. Over immense timescales, all organized structures decay. Physicists in the 19th century first realized this could imply a terrifying future, sometimes called heat death. Lord Kelvin discussed versions of the idea over 150 years ago, long before modern cosmology fully existed. The concept suggested the universe might someday reach maximum thermodynamic equilibrium, where no meaningful work could occur anymore. At the time, many people hated the idea. An eternal static universe felt comforting. A dying, exhausted cosmonaut, you float farther ahead, and galaxies themselves begin physically changing. Over incredible spans of time, gravitational interactions slowly eject stars from galaxies entirely. Some stars gain velocity through close encounters and drift alone through intergalactic darkness forever. Rogue stars, homeless suns wandering empty space with frozen dead planets still orbiting them. Fringe astrophysical theories even speculate that advanced civilizations might deliberately move between stars using gravitational assists from black holes, essentially surfing cosmic mechanics to survive longer in the aging universe. Which is either genius-level engineering or the most stressful road trip imaginable. You continue through the fading cosmos, while ancient white dwarfs cool further into hypothetical black dwarfs, cold, dark stellar remnants that emit virtually no light at all. Interestingly, the universe is not old enough for any black dwarfs to exist yet. Not even close. Right now, existence still sits in its comparatively youthful era. But youth is temporary. Around you, fewer stars ignite, more stars die. The darkness between galaxies stretches wider every moment. Cosmic expansion steadily isolates every remaining island of light. And somewhere far ahead, beyond even this dying age of stars, the black holes are waiting patiently for their turn to inherit the universe. The stars have mostly disappeared now. You drift through a universe lit less by suns and more by remnants. Ancient white dwarfs glow faintly like cooling ashes. Neutron stars spin silently in darkness. Rogue planets wander without parent stars at all. Frozen worlds tumbling endlessly through black space. And everywhere, black holes wait. This is becoming their universe. You approach one slowly now, suspended in the emptiness like a tear in reality itself. No surface, no solid shape. Just gravity so intense that not even light escapes once it crosses the event horizon. The black hole doesn't look like a hole exactly. It bends the surrounding starlight into warped rings and distorted halos. Space itself curves around it like stretched fabric pulled toward an invisible drain. Honestly, if the universe had a final boss, this would probably be it. Black holes form when massive stars collapse under their own gravity after exhausting nuclear fuel. Without outward pressure from fusion, the star caves inward catastrophically. Matter compresses beyond ordinary understanding into an infinitely dense point called a singularity, at least according to classical physics. Though physicists quietly admit the singularity probably means their equations have started emotionally unraveling. You continue drifting through this far future cosmos where black holes now dominate galactic centers and interstellar space alike. Over trillions upon trillions of years, they consume wandering stars, gas clouds, dead stellar remnants, and occasionally one another. Some become unimaginably enormous. Supermassive black holes already exist in the modern universe. The black hole at the center of the Milky Way contains about 4 million times the mass of the Sun. Other black holes are vastly larger still. Some quasars in the early universe appear powered by black holes containing billions of solar masses. In this future era, mergers continue building them into even greater monsters. You watch two giant black holes spiral toward each other now. Their orbit tightens gradually, while space-time ripples outward in gravitational waves. Eventually, they collide in a violent burst of distorted gravity, merging into one larger black hole that settles with a final shudder through reality itself. No explosion, no fire, just gravity rearranging the architecture of the universe. The first direct detection of gravitational waves happened in 2015 through the LIGO Observatory, confirming a prediction Albert Einstein made a century earlier. Historians still argue whether Einstein himself fully believed black holes physically existed or considered them mathematical oddities. Either way, reality turned out stranger than expected. Again, you move closer toward the event horizon. Time itself behaves differently here. According to relativity, clocks near strong gravity run slower relative to distant observers. If someone watched you approach the horizon from far away, they'd see your movements slow gradually, your light redshifting and fading. From your own perspective, though, you simply continue inward. Physics becomes deeply weird around black holes. Matter falling toward them heats into blazing accretion disks, hotter than many stars. Magnetic fields twist violently. Jets of radiation erupt outward at nearly light speed across intergalactic distances. And yet the black hole itself remains perfectly dark. There's an eerie elegance to them. They are simultaneously simple and terrifying. According to the no-hair theorem, black holes are defined only by mass, charge, and spin. Everything else about the matter that formed them gets erased behind the event horizon. The universe's most aggressive delete button. You continue farther into time. By now, ordinary star formation has nearly ceased entirely. The remaining cosmos belongs to stellar remnants and black holes. Occasional gravitational encounters send dead objects spiraling inward to be consumed. A white dwarf drifts too close. You watch tidal forces stretch it apart into glowing ribbons of matter circling the black hole, like luminous paint swirling down a drain. Radiation briefly flares across the darkness before fading again into silence. Then stillness returns. This age of black holes may last longer than all previous cosmic eras combined. That part is difficult to fully absorb. Humanity's entire recorded history spans only a few thousand years. Dinosaurs vanished 66 million years ago. The Sun itself may live 10 billion years total. But black hole eras unfold across timescales so absurd they make even stellar lifetimes seem brief. Some calculations suggest supermassive black holes could survive for around 10⁻⁴ years before finally disappearing. That's a 1 followed by 100 zeros, a number so huge it barely feels connected to normal existence anymore. A quirky fringe idea once proposed that advanced civilizations might upload themselves into black holes to exploit extreme time dilation and survive longer subjectively. Physicists remain deeply skeptical about that plan, mostly because coming inside a gravitational abyss tends to complicate long-term survival strategies. Still, humans do love terrible ideas with confidence. You float through vast regions where almost no visible light remains. Occasionally, a dead stellar remnant collides with another. Sometimes black holes merge, but increasingly, the universe grows dark and cold. Entropy keeps winning. Even black holes themselves are not eternal, though most scientists once believed they were. For decades, physicists assumed nothing could escape them at all. Then Stephen Hawking changed everything. In the 1970s, Hawking combined quantum mechanics with relativity and discovered something astonishing. Black holes should slowly emit faint radiation due to quantum effects near the event horizon. This process, now called Hawking radiation, means black holes gradually lose mass over unimaginable timescales. At first, the idea sounded almost absurd, a black hole evaporating, but the mathematics held, and that means even these gigantic rulers of the late universe carry the seeds of their own destruction. You drift beside a supermassive black hole while tiny particles of Hawking radiation leak invisibly into surrounding darkness. The process is unbelievably slow at first. For massive black holes, the emitted radiation is colder than the cosmic microwave background itself. But eventually, after incomprehensible ages pass, the background universe cools further, and then the black holes begin to die, quietly, patiently. One impossible fraction of energy at a time. The universe is almost unrecognizable now. You drift through darkness so complete, it barely feels like space anymore. Galaxies are gone beyond the horizon. Stars have nearly vanished. Even the great black holes that inherited the cosmos have begun their impossibly slow decline. And yet, against all instinct, something still happens here. Tiny whispers of energy leak from the darkness. Stephen Hawking's discovery changed the fate of the universe forever because it revealed that black holes are not truly eternal. Quantum mechanics refuses to allow absolute stillness. Near the event horizon, space itself churns with temporary particle pairs, constantly appearing and vanishing. Normally, these particles annihilate instantly, but near a black hole, gravity can separate them before they reconnect. One falls inward. The other escapes into space. To distant observers, it appears as though the black hole emits radiation and slowly loses mass over time, Hawking radiation, a process so faint and slow that a stellar mass black hole today would take vastly longer than the current age of the universe to evaporate completely. But eventually, given enough time, even the darkest objects in existence fade away. You float near one now during its final era. The black hole no longer feeds on stars because there are almost none left nearby. Intergalactic space has become nearly empty. The cosmic microwave background, leftover heat from the Big Bang, has cooled toward absolute zero, so the black hole radiates very slowly at first, then faster as it loses mass. Curiously, smaller black holes evaporate faster than larger ones. As they shrink, their temperature rises, causing them to emit radiation more rapidly. The process accelerates toward the end, like cosmic reverse aging, which feels unfair, honestly. Humans spend fortunes trying to look younger, while black holes accidentally achieve it through quantum mechanics. You continue drifting across stretches of empty space, where ancient black dwarfs lie frozen and invisible. These hypothetical remnants were once white dwarf stars, but after trillions of years, they cooled completely into dark objects emitting virtually no heat or light. No black dwarfs exist yet in the present universe, because the cosmos simply isn't old enough. That fact alone gives you a strange sense of perspective. Everything humanity has ever known still belongs to the opening moments of cosmic history. You are embarrassingly early. Nearby, one black hole finally reaches its last moments after an almost incomprehensible lifespan. Its mass has dwindled enormously. Radiation pours outward in increasingly energetic bursts. Then suddenly a flash, a final eruption of particles and energy. And the black hole disappears completely, not with thunder, not with triumph, just one brief pulse fading back into silence. You watch the empty region where it once existed. Space closes calmly around the absence, as though nothing extraordinary happened at all. Historians still argue whether Hawking radiation fully resolves the famous information paradox, one of modern physics' deepest mysteries. If black holes erase information completely, quantum mechanics breaks down. But if information somehow survives evaporation, scientists still don't fully understand how. Some physicists suspect information escapes subtly through Hawking radiation itself. Others believe entirely new physics may emerge near event horizons. The universe, as usual, declines to explain itself clearly. You drift farther ahead through time periods so enormous that ordinary numbers become meaningless. Black holes continue evaporating one by one across the darkness. The largest survive longest. Supermassive giants linger like ancient kings refusing to leave empty kingdoms. But eventually they too disappear. The cosmos grows quieter still. This is approaching the era physicists call heat death. Not an explosion, not collapse, not dramatic destruction, simply equilibrium. Entropy has been climbing since the beginning of time, and now it approaches its final victory. Energy spreads evenly across space. Temperature differences vanish. Useful work becomes impossible because nothing remains organized enough to power change. No stars burn, no planets warm, no civilizations build. The universe reaches maximum thermodynamic disorder, and somehow that ending feels more unsettling than violence. You pass through ancient regions where matter itself has begun decaying. Some grand unified theories predict protons may not be truly stable forever. If proton decay occurs, even atoms eventually disintegrate into lighter particles over staggeringly long timescales. A chair would not rot, a mountain would not erode. Matter itself would simply stop existing piece by piece, though scientists still debate whether proton decay actually happens. Experiments deep underground continue searching for evidence today, waiting patiently beside giant tanks of ultra-pure water and sensitive detectors. So far, protons appear annoyingly committed to remaining intact. Stubborn little things. You float onward through nearly frozen space, while isolated photons drift endlessly through darkness. Electrons and positrons occasionally collide and annihilate. Sparse particles interact once every unimaginable span of time. The universe becomes thin, cold, silent. There's almost something peaceful about it now. No explosions disturb the void anymore. No galaxies collide. No new stars ignite beneath glowing nebulae. The frantic, energetic youth of the cosmos ended long ago. Only faint radiation remains. A quirky fringe concept known as Boltzmann brains emerges from this late universe physics. Some theorists speculate that in an eternally empty cosmos, random quantum fluctuations might occasionally assemble self-aware minds temporarily out of chaos, spontaneously appearing in darkness with fabricated memories before instantly vanishing again, which honestly sounds less like cosmology and more like forgetting why you walked into a room. Most physicists dislike the Boltzmann brain problem intensely because it creates bizarre philosophical implications about observation and probability. Yet the mathematics lingers uncomfortably in certain models of eternal universes. You continue drifting through the nearly dead cosmos, while time stretches onward almost pointlessly. Without stars or civilizations or major events, duration itself loses meaning. There are no sunsets to measure days, no orbital cycles, no biological clocks, just emptiness expanding forever. And still the universe keeps going. That may be the strangest part of all. Even after everything familiar disappears, existence itself continues lingering in the dark, carrying faint whispers of energy across a frozen endless sea where black holes once ruled like gods. Now even they are gone. The universe has become still, not completely motionless, of course. Particles still drift, Quantum fluctuations still tremble faintly beneath reality, like tiny ripples under black ice. But compared to the roaring, energetic cosmos you once knew, this future feels almost hauntingly calm. You float through the era physicists fearfully call heat death. The name sounds dramatic, but the reality is stranger than fire or destruction. Heat death does not mean everything burns. It means the opposite. Energy spreads so evenly throughout the universe that nothing useful can happen anymore. No engines run, no stars shine, no life gathers warmth against the cold. Entropy has finally reached near maximum. You drift across distances so vast that entire galaxies once existed between the lonely particles surrounding you now. Space continues expanding relentlessly under the influence of dark energy. The observable universe has swollen into something almost incomprehensibly empty. A photon passes nearby after traveling alone for longer than human language could possibly describe. It carries ancient, diluted energy stretched thin by cosmic expansion, like a fading echo from a reality that once mattered. And honestly, the universe at this stage feels less dead than forgotten. That's the unsettling part. You continue onward, through darkness, approaching absolute zero temperature. Modern scientists estimate the current universe sits around 2.7 Kelvin due to the cosmic microwave background radiation left over from the Big Bang. But in this far future era, even that faint heat has nearly vanished. Cold dominates everything now. Not icy winter cold, not mountain at night cold. The kind of cold where molecular motion itself nearly stops. You pass isolated electrons drifting through endless emptiness. Occasionally sparse particles interact, but events become absurdly rare. Entire stretches of time longer than all previous cosmic history may pass without anything significant occurring nearby. Imagine waiting 10 trillion years just for one particle collision. At that point, even patience probably gives up. Still, physicists remain fascinated by this final thermodynamic state, because it emerges naturally from the laws governing entropy. The second law of thermodynamics quietly pushes systems toward equilibrium. Hot objects cool. Energy disperses. Order dissolves into randomness. The universe itself obeys the same rule. 19th century physicist Rudolf Clausius helped formalize entropy mathematically, leading scientists toward the startling realization that the cosmos might possess a one-way direction toward exhaustion. Historians still argue whether Victorian scientists emotionally struggled with heat death because it challenged religious and philosophical ideas about eternal purpose. Probably yes. It's difficult to feel cosmically optimistic while studying equations predicting infinite boredom. You drift farther through the dark while remnants of matter continue decaying. If proton decay truly occurs, then eventually even atomic structure fails entirely. Matter dissolves into lighter particles and radiation over staggeringly immense timescales. Everything solid disappears. Mountains, planets, ancient spacecraft. That one sock missing from your dryer somehow still probably survives longer than expected, though. Fringe cosmological theories occasionally suggest intelligent civilizations might attempt survival by dramatically slowing subjective consciousness to conserve energy during heat death. Theoretical beings could hibernate for billions of years between moments of activity, stretching finite energy reserves across unimaginable durations. Like cosmic bears trying to outweigh entropy itself, whether such survival is physically possible remains deeply uncertain. You continue through this nearly empty future while dark energy keeps pulling space wider apart. Galaxies no longer interact because the distances between remaining structures have grown impossibly large. Every surviving island of matter becomes isolated beyond causal contact. Loneliness itself turns cosmic. And yet quantum mechanics still refuses absolute silence. Tiny fluctuations constantly appear even in vacuum states. Empty space is not truly empty. Virtual particles flicker briefly into existence before annihilating again. The vacuums see these invisibly with microscopic uncertainty. This bizarre fact shocked physicists throughout the 20th century. Reality, at its deepest level, behaves less like stable machinery and more like probabilistic turbulence. Even nothingness has noise. You drift through regions where occasional low-energy photons cross paths after traveling for unimaginable spans of time. Rare interactions release tiny flashes of radiation before fading instantly back into darkness. These may become among the final visible events in the cosmos, little sparks in an ocean of black. A quirky modern idea called the omega point once proposed that advanced intelligence might eventually harness the entire collapsing universe into infinite computation near a final singularity. Most cosmologists today remain skeptical because accelerating expansion appears incompatible with that scenario. Still, humanity deserves points for creativity. When confronted with eternal cosmic death, the human brain apparently responds by inventing increasingly elaborate science fiction survival plans. You continue floating through the immense silence, while time itself begins feeling philosophically strange. In ordinary life, time gains meaning through change. Days pass because sunlight shifts, bodies age, clocks tick, hearts beat. But here, almost nothing changes anymore. Without events to measure duration against, the distinction between 1 trillion years and another starts becoming abstract. Time stretches onward mathematically, yet experientially the universe feels frozen. Some physicists and philosophers even debate whether time retains meaningful existence in maximum entropy states. Historians still argue whether time fundamentally requires irreversible processes to remain physically meaningful at all. The debate remains unresolved. Because of course it does. You drift onward beside scattered particles left behind by vanished stars and evaporated black holes. The universe no longer resembles a place built for life or structure. It has become diffuse radiation spread thinly across endless expansion. And yet there is a strange beauty here too. The chaos is gone. The violence is gone. No supernovas erupt. No black holes consume stars. No galaxies collide beneath blazing arcs of light. The cosmos has entered a final quiet equilibrium, almost meditative in its stillness, a dark ocean after the storm. But somewhere within modern physics, another possibility waits uneasily in the equations. Because some scientists suspect the universe may not simply fade peacefully into heat death. Some think dark energy could become far more dangerous than anyone imagined. And if they are right, the ending ahead is not silence. It is tearing. At first, the change seems harmless. You drift through the far future universe, still cold, still sparse, still expanding quietly into darkness. But something subtle begins accelerating beneath the emptiness itself. Space is stretching faster than before, much faster. And unlike the calm fading stillness of heat death, this future carries a growing tension beneath it, like hearing ice crack beneath your feet while crossing a frozen lake at night. This is the nightmare scenario cosmologists call the Big Rip. The idea emerges from one unsettling possibility. What if dark energy does not remain constant over time? What if the mysterious force driving cosmic expansion actually grows stronger? If that happens, the universe does not merely drift apart peacefully, it gets torn apart. You move forward through accelerating epochs, while galaxies begin separating more violently than before. Normally, gravity binds galaxies together internally, even as space expands between them. But in the Big Rip scenario, expansion eventually becomes so powerful that gravity can no longer hold large structures intact. Galaxy clusters dissolve first. Massive systems containing thousands of galaxies slowly unravel as space stretches faster than gravity can compensate. Entire galaxies drift apart into isolation. The cosmos starts coming undone at the seams. Dark energy itself remains one of modern science's greatest mysteries. Astronomers first discovered accelerating expansion in 1998 while studying distant-type supernovas. The findings shocked the scientific world because, Gravity was expected to slow cosmic expansion over time, not accelerate it. Instead, the opposite appeared true. Some physicists describe dark energy as an intrinsic property of empty space itself. Others suspect entirely new physics may be involved. Historians still argue whether dark energy represents a cosmological constant, a dynamic field, or evidence that our understanding of gravity remains incomplete. Which is scientist language for, we are deeply confused but trying our best. You continue drifting deeper into the Big Rip timeline. Millions of years pass, then billions. Expansion accelerates further. Galaxies outside your local region disappear not merely because of distance now, but because spacetime itself expands with mounting aggression. The observable universe shrinks toward only nearby structures. Eventually, even those structures destabilize. You watch stars inside galaxies begin separating from one another as gravitational binding weakens. Spiral arms dissolve, stellar orbits fail, ancient galaxies unravel into scattered streams of lonely stars drifting through rapidly expanding darkness. The night sky changes catastrophically, constellations vanish, neighboring stars disappear. One by one, every familiar pattern breaks apart, and the expansion keeps accelerating. You pass near a future planetary system, orbiting a dim red dwarf star, one of the last surviving stellar types in existence. Even here, gravity begins losing the battle. Planets drift farther from their parent star. Orbits destabilize. The star itself cannot hold its system together forever. A fringe physics tidbit from the early 21st century suggested phantom energy, a hypothetical extreme form of dark energy, might drive expansion so violently that the universe reaches infinite expansion within finite time. Many cosmologists remain skeptical of phantom energy models, but the mathematics remains disturbingly possible. Sometimes the equations themselves sound nervous. You move farther ahead. The timeline toward destruction speeds up now. In some Big Rip models, galaxies disintegrate billions of years before the final moment. Solar systems break apart mere months beforehand. Planets themselves rupture minutes before the end. Then things become truly horrifying. Gravity inside planets fails. Molecules separate. Atoms themselves tear apart. Imagine space stretching so violently that even matter cannot remain connected. You watch a planet crack silently beneath impossible tidal expansion. Oceans lift into vapor. Mountains unravel. The planet elongates grotesquely before dissolving entirely into streams of particles scattered across expanding space-time. And still the tearing continues. Eventually even atoms cannot survive. Electrons lose attachment to nuclei. Matter dissolves into elementary particles suspended inside runaway expansion. The universe stops being a place containing objects. It becomes expansion itself. Honestly, it feels less like destruction and more like reality, forgetting how to stay assembled. You drift through the final stages now, where distances between points in space increase infinitely fast. Light itself struggles to cross regions before those regions stretch apart further. Causality breaks down. Communication becomes impossible. Every surviving particle becomes isolated from every other. Physicists sometimes calculate hypothetical countdowns for the Big Rip under specific dark energy assumptions. In one famous model proposed by Robert Caldwell and colleagues, the final destruction sequence accelerates dramatically near the end, with larger structures failing first and smaller structures shortly afterward. Thankfully, current observations still suggest ordinary cosmological constant behavior remains more likely, probably, hopefully, maybe. You continue floating through the tearing cosmos while space-time itself destabilizes around you. There are no explosions because explosions require matter remaining locally connected long enough to transfer energy coherently. Here, even locality starts dissolving. Time behaves strangely too. As the final singularity approaches, physical intervals compress toward the ultimate endpoint. The universe races toward destruction with terrifying acceleration. And yet from another perspective, this ending possesses a strange elegance. The Big Rip represents the ultimate triumph of expansion over gravity. Since the Big Bang, those two forces shaped cosmic history together, gravity pulling inward, expansion carrying outward. Now expansion wins completely. No survivors, no remnants, no black holes lingering in darkness. Even they eventually rip apart under sufficient expansion. That detail unsettled many physicists when the theory first appeared. Black holes often seem like eternal cosmic fortress immune to ordinary destruction. But in the Big Rip scenario, not even space-time curvature can resist indefinitely. Everything loses. You approach the final moments now. Galaxies are gone, stars are gone, planets are gone, atoms are gone. Only rapidly expanding fields remain inside space-time, stretching toward infinite separation. Then, the equations themselves stop making sense. Bonds breaks down at the endpoint. No one knows what happens beyond it. Perhaps nothing. Perhaps new physics emerges. Perhaps reality itself ends entirely. And somewhere back in the long-dead ancient universe, humans once worried about paying bills on time, while all this waited silently in the far future. Perspective really is brutal sometimes. But not every scientist believes the universe ends by tearing itself apart. You drift backward from the chaos of the Big Rip into another possibility entirely. One older and strangely more symmetrical. A future where expansion eventually slows, stops, reverses. A universe that falls back inward. This is the Big Crunch. And unlike the cold loneliness of heat death or the violent unraveling of the Big Rip, the Big Crunch feels almost mythological, ancient, cyclical, like the cosmos inhaling after an impossibly long exhale. You float through deep time while gravity quietly continues tugging on everything in existence. Every galaxy pulls on every other galaxy. Every particle influences space-time around it. In the early 20th century, many cosmologists assumed gravity would eventually slow expansion enough to halt it completely. The real question was simple. Does the universe contain enough matter to pull itself back together? For decades, scientists debated this intensely. The fate of existence appeared balanced on a cosmic accounting problem. Too little matter, and expansion continues forever. Enough matter, and eventually the universe reverses course. You drift farther into this hypothetical future. At first, the changes are subtle. Galaxies still separate, but more slowly now. Expansion loses momentum bit by bit as gravity pushes back across unimaginable distances. The universe reaches maximum size like a ball tossed upward, finally pausing at the peak of its arc. Then, everything changes direction. Galaxies begin approaching one another. The night sky slowly grows brighter instead of darker. Distant light shifts blueward as space contracts. Ancient isolated galaxies return gradually into visibility after trillions of years apart. Honestly, after so much cosmic loneliness, it almost feels weirdly comforting. You move through the contracting universe while galaxy collisions become increasingly common. Massive structures merge repeatedly. Black holes consume growing amounts of matter. Radiation intensifies throughout space as the cosmos compresses. Temperature rises, density increases. The universe begins remembering its violent youth. Historians still argue whether early supporters of the Big Crunch were influenced partly by philosophical preferences for cyclic models of reality. A universe with rebirth feels emotionally different. From one ending in eternal silence, humans seem deeply attached to stories where endings become beginnings again, possibly because nobody enjoys hearing everything fades forever right before bedtime. You continue drifting inward through cosmic collapse. Stars form rapidly once more as compressed gas clouds ignite across crowded galaxies. The sky becomes dazzlingly bright. Radiation fills space. Distances between objects shrink continuously. The entire cosmos feels crowded now, claustrophobic even. Imagine every galaxy in existence, slowly moving toward every other galaxy at once. Traffic would be absolutely unbearable. Meanwhile, black holes grow enormous from endless mergers and infalling matter. Supermassive black holes collide repeatedly, warping space-time with gravitational waves, more powerful than anything seen during earlier cosmic eras. The universe becomes hot again, very hot. Eventually, galaxy structures themselves cannot survive the compression. Matter crowds together too densely. Cosmic background radiation intensifies dramatically as wavelengths shorten during contraction. You drift through a universe increasingly resembling conditions shortly after the original Big Bang. Except now everything moves inward rather than outward. Some cosmologists once proposed the Big Crunch might end in a final singularity, mirroring the beginning of the universe itself. Space shrinks toward infinite density. Temperature rises beyond comprehension. Physics equations collapse under extreme conditions. Essentially, reality crashes into itself. A quirky fringe tidbit from 20th century cosmology suggested intelligent civilizations might attempt to manipulate collapsing cosmic conditions to preserve information into whatever comes next. Freeman Dyson and other speculative thinkers explored bizarre long-term survival concepts involving computation during cosmic collapse, because apparently humans see universal destruction and immediately start brainstorming backup plans. You continue toward the final stages of contraction. Stars cannot survive now. Galaxies lose structure entirely. Matter compresses into increasingly dense states. Atomic nuclei break apart beneath immense temperatures and pressures. Then even those structures fail. Particles collide constantly inside the shrinking cosmos. Energy densities soar higher and higher. The universe becomes an ocean of radiation and elementary particles compressed into a rapidly collapsing space-time. And still gravity pulls inward. At this point, modern physics becomes deeply uncertain. General relativity predicts singularities under extreme collapse, but quantum mechanics strongly suggests singularities represent incomplete understanding rather than literal infinities. Scientists still lack a full theory of quantum gravity, capable of describing these conditions accurately. The equations begin arguing with each other, loudly. You drift closer toward the endpoint where all distances shrink toward nothing. Every galaxy that ever existed, every star, every atom, every memory, every civilization, all collapsing together. The scale feels impossible emotionally. Humanity often imagines itself important because individual lives feel large from the inside. But here the entire observable universe compresses into something potentially smaller than a subatomic particle. Reality itself folds inward. Yet strangely, this may not be the end. Some physicists suspect a collapsing universe could trigger another expansion event, another Big Bang, a cosmic rebound. A bounce, the idea remains speculative, but it transforms the Big Crunch from a final destruction into a transition between universes. Death becoming rebirth. You approach the final collapsons now, while space-time curves beyond ordinary imagination. Heat floods everything. Quantum effects dominate reality itself. The cosmos contracts toward conditions so extreme that familiar concepts like distance and time begin losing meaning. Then, possibility opens. Maybe the universe ends here forever. Maybe a new universe erupts from the collapse. Maybe every Big Bang emerges from the death of a previous cosmos, stretching infinitely backward through endless cycles. No one knows. And that uncertainty lingers at the edge of modern cosmology like a half-seen shape moving in darkness. Because the deeper you travel into the fate of the universe, the stranger the answers become. You drift beyond the collapse now, or perhaps beside it, or perhaps after it. At this scale, ordinary language starts failing quietly in the corner while physics scribbles desperate notes across chalkboards. The universe may not die only once. That possibility emerges from one of cosmology's strangest and most persistent ideas, the cyclic universe. A reality where cosmic beginnings over and over again, endlessly repeating through unimaginable epochs, birth, expansion, death, rebirth. again and again, like some colossal breathing pattern older than time itself. You float through the aftermath of a collapsing cosmos where density rises toward impossible extremes. Classical physics predicts a singularity here, an infinitely compressed point where equations stop functioning properly. But many physicists dislike infinities intensely. Infinity in equations often signals incomplete understanding rather than physical truth. So scientists began wondering whether something prevents total collapse at the final instant. Quantum mechanics may provide the answer. In some theoretical models, quantum effects generate a repulsive force under ultra-extreme densities, halting collapse before a true singularity forms. Instead of ending in infinite compression, the universe rebounds outward in another big bang, a big bounce. You watch it happen now. The collapsing cosmos compresses hotter and denser until suddenly expansion erupts outward once more. Space itself blossoms rapidly from microscopic scales into vast dimensions. Energy floods reality. Particles form. Radiation surges outward. Another universe begins, not inside space. As space, honestly, the whole process feels suspiciously like the universe, repeatedly smashing its own reset button. Modern cyclic cosmology has roots stretching surprisingly far into history. Ancient Hindu traditions described recurring cosmic cycles called kalpas, vast repeating ages of creation and destruction unfolding eternally. Some Stoic philosophers in ancient Greece imagined periodic cosmic rebirth through universal fire. Historians still argue whether these ancient cyclical myths reflected deep philosophical intuition or simply humanity projecting natural seasonal cycles onto the cosmos itself. Either way, humans have apparently suspected reality might recycle itself for thousands of years. You drift through this newborn universe while fundamental particles condense from searing energy fields. Quarks bind into protons and neutrons. Hydrogen forms. Gravity slowly gathers matter into the first stars and galaxies once more. It looks hauntingly familiar, perhaps because our own universe may have emerged this way. One modern cyclic proposal, called the ekpyrotic model, suggests our universe exists on a three-dimensional brane, floating inside higher dimensional space. According to the theory, cosmic rebirth occurs when parallel branes collide, triggering Big Bang-like expansion events repeatedly over immense timescales, which sounds less like astronomy and more like two invisible cosmic pancakes slamming together in another dimension. Things gets wonderfully strange when pushed far enough. You continue drifting through repeating cosmic ages where universes expand, age and collapse across endless sequences. Each cycle may differ slightly from the last. Tiny quantum variations ripple outward into entirely different cosmic histories. Perhaps some universes form more galaxies. Perhaps others collapse quickly. Perhaps some never produce life at all. And perhaps somewhere, another version of humanity once sat beneath another Milky Way, asking the exact same questions. The idea unsettles people for different reasons. Some find cyclic cosmology comforting because it removes the idea of a final absolute ending. Others find it terrifying because repetition without escape feels deeply existential in its own way. Infinite universes, infinite deaths, infinite beginnings, no final conclusion, just eternal recurrence. You move farther through the bouncing cosmos, while inflationary expansion rapidly smooths space after rebirth. This inflationary period was first proposed in the early 1980s to explain why the universe appears remarkably uniform across enormous distances. Tiny quantum fluctuations during inflation may later become galaxies themselves. That means every galaxy, every star, every planet, and every living thing ultimately traces back to microscopic quantum irregularities, amplified across cosmic history. The universe literally exists because tiny fluctuations refuse to remain quiet. Relatable, honestly. A quirky fringe interpretation of cyclic cosmology proposes that entropy somehow resets between cosmic bounces, avoiding the thermodynamic problem of infinite disorder accumulation. Critics argue this remains difficult mathematically because entropy normally increases relentlessly. The debate remains unresolved because the universe enjoys keeping cosmologists unemployed forever. You continue drifting between cycles now, where time itself becomes difficult to define clearly. If every universe emerges from a previous collapse, then does time stretch infinitely backward? Was there ever a true beginning? Some physicists suspect the question itself may be flawed. Perhaps beginnings only exist locally within individual cosmic cycles, while the larger structure remains eternal. Others argue quantum gravity may eventually reveal an absolute origin beneath all cycles after all. No consensus exists, only possibilities. You float beside another newborn universe, while stars begin igniting across pristine galaxies. Heavy elements form inside stellar cores. Planets condense from dust. Somewhere oceans may gather beneath alien skies. Life may emerge again. Maybe differently, maybe not. There's something strangely peaceful about imagining cosmic rebirth after so much discussion of endings. The universe transforms from a doomed structure into an ongoing process, less like a machine breaking down, and more like tides endlessly rising and falling. But not all physicists accept cyclic models. Some argue accelerating expansion from dark energy makes future collapse impossible. Others point out serious, unresolved problems involving entropy and quantum behavior near bounce conditions. And meanwhile, another terrifying possibility waits silently inside quantum field theory. A possibility far more sudden than heat death, far more unpredictable than the Big Crunch. Because according to some equations, the universe may not need billions of years to end at all. It could happen instantly, without warning, without mercy, like a trapdoor hidden beneath reality itself. The universe seems stable. That's the comforting assumption quietly supporting your entire existence right now. The atoms in your body hold together. Space behaves predictably. Physics follows consistent rules from one moment to the next. But what if all of that stability is temporary? You drift into one of the most unsettling ideas in modern cosmology: vacuum decay. A theory so strangely terrifying that even physicists sometimes discuss it with the careful tone people use when talking about cracks in a dam. Because according to quantum field theory, the universe may be balanced in a state that only appears stable, a false vacuum. Imagine placing a ball in a shallow dip on a hillside. From nearby, the ball looks secure, stable, permanent even. But somewhere lower down the hill exists a deeper valley. If the ball ever receives enough disturbance, it suddenly rolls downward into a completely new state. Vacuum decay proposes reality itself may work similarly. The quantum fields underlying the universe could currently occupy a metastable state rather than the true lowest energy configuration. If that's true, then somewhere, someday, a transition to a lower energy vacuum could occur. And the consequences would be catastrophic beyond imagination. You float through empty intergalactic darkness while quantum fields shimmer invisibly beneath space-time. These fields define the fundamental structure of reality itself. Every particle emerges from them. Every force depends on them. Champ the vacuum state, and you change the laws governing existence. Instantly. The frightening part is how ordinary the universe appears beforehand. No warning sirens. No trembling skies. One moment reality functions normally. The next moment, a bubble of true vacuum forms somewhere in space. Then it expands outward at nearly the speed of light, diding everything it touches. Honestly, the universe really did save some of its worst ideas for quantum physics. The modern discussion of vacuum stability intensified after the discovery of the Higgs boson in 2012 at CERN. Measurements of the Higgs field and top quark mass suggested our universe may sit disturbingly close to the boundary between stability and metastability. Not definitely doomed, but maybe uncomfortably balanced. You continue drifting while physicists debate the implications. Historians still argue whether vacuum decay scenarios represent physically meaningful threats or merely artifacts of incomplete models at extremely high energies. Most scientists emphasize there is no reason for immediate panic, which is exactly what you'd expect people to say moments before a cosmic disaster movie begins. You move deeper into the theory now. A true vacuum bubble appears somewhere unimaginably far away. Inside this bubble, the fundamental constants of nature differ from those outside. Particle masses change, electromagnetic interactions shift, chemistry itself may become impossible. Atoms cannot survive the transition, neither can stars, nor planets, nor biology. The bubble expands relentlessly at almost light speed because lower energy vacuum states remain energetically favored. And since nothing travels faster than light, no observer ahead of the bubble can detect it approaching. You would never see it coming. That detail alone makes vacuum decay uniquely disturbing among cosmic endings. Heat death unfolds slowly across trillions of years. The Big Crunch provides warning through collapsing galaxies. Even the Big Rip escalates progressively. Vacuum decay simply arrives, instantly, like reality deleting itself without bothering to announce the update. You drift beside a hypothetical expanding vacuum bubble now. Its boundary glows strangely against surrounding space, though in reality, no human observer could ever witness such a thing directly before destruction occurred. Inside the bubble, physics rewrites itself. Perhaps atoms cannot form there. Perhaps stable matter becomes impossible. Perhaps space-time itself behaves differently beyond comprehension. Some theories even suggest the bubble could alter the number of spatial dimensions or eliminate forces entirely. A quirky fringe speculation once proposed that advanced civilizations might attempt to artificially trigger new universes through vacuum transitions, essentially creating baby cosmos inside high-energy conditions near black holes. Most physicists remain skeptical, partly because accidentally destroying reality tends to create difficult ethical paperwork. You continue through this unsettling quantum landscape, while uncertainty itself dominates the discussion. Vacuum decay depends heavily on incomplete physics, near energy scales humanity cannot experimentally probe directly. And yet the mathematics refuses to disappear. That's what makes theoretical physics simultaneously fascinating and mildly horrifying. Sometimes equations imply possibilities nobody wanted to imagine. You drift farther while empty space crackles faintly with virtual particles flickering in and out of existence. Quantum mechanics never allows perfect stillness. Reality behaves probabilistically at its deepest levels. Tiny fluctuations constantly occur everywhere, usually harmless. Probably meanwhile, cosmologists continue debating whether inflationary multiverse models affect vacuum stability. Some theories suggest countless universes may exist with different vacuum states and physical constants. Our universe could simply occupy one temporary region within a vastly larger cosmic landscape. If true, vacuum decay bubbles might already form somewhere beyond our observable horizon. Cheerful thought before sleep. You move onward through darkness while the fragile elegance of existence becomes impossible to ignore. Every stable atom, every orbiting planet, every living organism depends on delicate balances between physical laws. Gravity precisely strong enough, electromagnetism carefully tuned. Quantum fields resting in apparently stable states. Reality feels less like solid architecture now, and more like an intricate balance act performed across cosmic scales. And somehow, despite all this fragility, the universe produced oceans, forests, consciousness, music, terrible reality television, and people arguing online about whether cereal counts as soup. Remarkable, really. You continue drifting through quantum uncertainty, while one final unsettling possibility emerges from the shadows of modern cosmology. Perhaps our universe is not unique at all. Perhaps countless others exist beyond it, different laws, different histories, different endings. And somewhere beyond the visible edge of space-time, entire other universes may already be drifting silently through a far larger reality has barely begun to imagine. You drift beyond the edge of the observable universe now. Not physically, perhaps, because the observable boundary is not a wall or barrier. It simply marks the farthest distance light has traveled since the Big Bang. Beyond it, space may continue endlessly, or maybe not. And that uncertainty opens the door to one of the strangest possibilities in modern cosmology. The multiverse. The idea sounds wildly fictional at first, like something invented by a sleep-deprived science fiction writer, surrounded by empty coffee cups and existential dread. But several serious branches of physics unexpectedly point toward the possibility that our universe may be only one region within a much larger cosmic structure, one bubble among countless others. You float through immense darkness while inflationary cosmology stretches space-time around you. According to inflation theory, the early universe expanded extraordinarily fast during its first tiny fraction of a second, faster than light itself, though relativity allows space to expand this way because nothing moves through space faster than light. Space itself stretches. That inflation explains several puzzling features of the universe remarkably well. It accounts for large-scale uniformity, flat geometry, and the origin of tiny fluctuations that later formed galaxies. NASA.gov. But inflation carries a strange implication. Some versions of the theory suggest inflation never completely stops everywhere. Instead, isolated regions stop inflating and form universes like ours, while the surrounding larger structure continues expanding eternally. New bubble universes constantly emerge inside an endlessly inflating background, an eternal cosmic foam. You drift beside one hypothetical newborn universe now. Inside it, space-time expands rapidly while particles and radiation condense into matter. Galaxies will eventually form here. Stars will ignite. Perhaps life will emerge beneath alien skies governed by unfamiliar physics. Because different universes may contain different laws entirely, that possibility changes everything. Maybe gravity varies elsewhere. Maybe atoms cannot form. Maybe some universes collapse instantly, while others expand forever. Some might contain 4 spatial dimensions, others none at all. And somewhere out there may exist universes where physics allows truly bizarre structures humanity cannot even conceptualize properly, which honestly feels rude after people spent centuries just trying to understand this universe. You continue drifting through the speculative landscape of eternal inflation, while countless bubble universes emerge across incomprehensible scales. Most remain forever causally disconnected from ours, because expansion between them outpaces any possible communication. They exist beyond reach, beyond observation, at least probably. Historians still argue whether multiverse theories qualify as if direct experimental verification remains impossible. Critics warn that unfalsifiable models risk drifting toward philosophy rather than physics. Supporters counter that if established equations naturally predict multiple universes, scientists cannot simply ignore the implication because it feels strange. And it definitely feels strange. A quirky fringe tidbit from quantum mechanics introduces another variation called the many worlds interpretation. Proposed by Hugh Everett in 1957, it suggests quantum events may split reality into branching parallel histories where every possible outcome occurs in separate worlds. Plato.stanford.edu. Meaning somewhere, theoretically, another version of you may currently be making better life decisions. Or worse ones, statistically probably both. You float through this endless cosmic landscape, while philosophers and physicists continue debating what the multiverse truly means. If infinitely many universes exist, then improbable events become inevitable somewhere. Entire histories repeat. Different versions of civilizations emerge under altered conditions. Perhaps somewhere another Earth exists orbiting another star, with another humanity staring upward asking identical questions about the fate of existence. The thought feels both comforting and deeply eerie. You continue drifting while dark energy expands your own universe farther into isolation. Even if other universes exist, crossing between them may prove permanently impossible. The observable cosmos becomes less like all existence and more like one tiny room inside a structure too enormous to fully map. And suddenly humanity feels very small again. Not meaningless, just small. There's a difference. For centuries, humans imagined themselves central to creation. Then astronomy revealed Earth was not the center of the solar system. Later discoveries showed the Sun was merely one star among billions in the Milky Way. Then the Milky Way became one galaxy among trillions. Now even the entire observable universe may be only one bubble among infinitely many others. Cosmology really does specialize in humbling people professionally. You drift farther, while strange theoretical structures appear in speculative physics. Brain cosmology imagines higher dimensional membranes floating through larger spaces. Quantum gravity models hint that space-time itself may emerge from deeper informational structures. Some physicists suspect reality resembles a hologram where three-dimensional space emerges from lower dimensional laws, which sounds suspiciously like the universe attended one philosophy class and never recovered. Meanwhile, another debate quietly continues beneath all these theories. Why does anything exist at all? Not galaxies, not stars, existence itself. Why do physical laws exist rather than nothingness? Why do quantum fields possess the values they do? Why is there a universe capable of complexity and life instead of eternal empty simplicity? Science explains mechanisms brilliantly, but ultimate origins remain elusive. You float through the silent multiverse, while universes bloom and fade like sparks in endless darkness. Some die through heat death, some collapse, some rip apart beneath runaway expansion. Others perhaps never survive long enough for stars to form. Reality becomes less like one story, and more like an infinite library filled with different cosmic fates. And somewhere inside all this vastness sits your tiny ancient civilization on a small rocky planet, orbiting an ordinary yellow star, briefly conscious long enough to wonder about the ending. That alone feels miraculous. Because after all the black holes, collapsing galaxies, entropy, vacuum decay, and endless cosmic darkness, one strange fact still remains. The universe became aware of itself, at least for a little while. The universe grows quiet again. After all the theories, all the collapsing stars and evaporating black holes and branching universes, floating through impossible dimensions, you eventually return to the simplest question of all. What remains at the very end? You drift through the fading future cosmos, while the last traces of light stretch thin across expanding darkness. The great galaxies are gone now, carried beyond reach by cosmic expansion, or reduced long ago to cold remnants and evaporated particles. Even black holes, those ancient rulers of the late universe, have vanished into faint Hawking radiation. Space itself feels enormous beyond comprehension, and almost empty, yet not completely empty. Quantum fluctuations still whisper beneath reality, like tiny ripples moving through a perfectly still ocean. Virtual particles continue appearing and disappearing. Fields tremble softly in the dark. The universe never becomes truly silent. That may be one of the strangest discoveries modern physics ever made. Vacuum itself contains structure. Empty space possesses energy. Even nothingness refuses to stay completely nothing. You float through this final era while isolated photons drift endlessly between distances so vast that words like far stop meaning much anymore. Time stretches onward without stars to measure it, without civilizations to record it, without planets turning beneath warm sun. Just duration, just existence continuing quietly. And somehow, despite all the terrifying endings you've witnessed tonight, there's a strange calm here now. Because the universe was never permanent. It was never meant to be frozen forever in one perfect state. From the first moments after the Big Bang, change was always written into reality itself. Stars lived by consuming themselves. Galaxies evolved through collisions. Even space-time carried the seeds of transformation forward across billions of years. Impermanence is not a flaw in the cosmos, it is the cosmos. Historians still argue whether human fear of cosmic endings reflects genuine existential anxiety, or simply the brain struggling against scales it was never designed to process. After all, your ancestors evolved to survive storms, predators, hunger, maybe one particularly aggressive goose near a riverbank, not the thermal destiny of the observable universe. And honestly, fair enough. You drift farther through the darkness while faint quantum fluctuations continue dancing invisibly beneath the vacuum. Some speculative theories suggest these fluctuations might eventually generate entirely new universes spontaneously. Tiny pockets of inflation, fresh Big Bangs emerging from apparent emptiness, reality beginning again somewhere beyond perception. Perhaps the cosmos is less like a story with one ending and more like an endless sea where universes rise and fade continuously like bubbles forming on dark water. No final curtain, no permanent conclusion. Just transformation. A quirky philosophical tidbit from ancient Buddhism taught that all compounded things eventually dissolve, an idea surprisingly resonant with modern entropy, despite emerging thousands of years before thermodynamics existed. Different civilizations across history sensed impermanence intuitively long before equations described it mathematically. The stars themselves simply confirmed the lesson later. You continue floating while the darkness softens around you. The terror of cosmic endings slowly fades into perspective. Because although the universe may someday grow cold or collapse or tear itself apart, right now it still contains warmth. Right now stars still shine, planets still turn, rain still falls on oceans beneath living skies. Somewhere tonight, people are laughing inside brightly lit kitchens. Someone is driving home under streetlights. Someone is staring upward through a telescope for the first time. Someone is falling asleep with this video, playing softly in the background, while a fan hums gently beside the bed. For a brief moment in cosmic history, the universe is awake, and so are you. You drift backward in memory now toward the younger cosmos again, toward spiral galaxies glowing blue with newborn stars, toward Earth orbiting quietly around its ordinary little sun, toward forests, clouds, cities, rivers, music, conversations, old photographs, forgotten dreams, tiny fragile things, but beautiful precisely because they do not last forever. That's the strange secret hidden beneath tonight's journey through cosmic death. Impermanence gives meaning to moments. A sunset matters because it fades. Music matters because notes disappear into silence. Lives matter because time moves forward. Even the stars understand this. One by one they burn through darkness, scattering the elements needed for planets and oceans and living minds capable of wondering where everything ends. You float now in complete stillness, while the final traces of cosmic light fade softly into blackness around you. No fear remains here anymore, only quiet, only distance, only the slow breathing rhythm of existence itself, stretching across eternity. And maybe somewhere beyond all current understanding, beyond entropy and vacuum decay and collapsing space-time, something new waits patiently in the dark. Another beginning, another universe, another sky filled with stars. The cosmos has ended many times tonight in many different ways. Frozen, torn apart, collapsed inward, dissolved through quantum instability. Yet every possibility carried one common truth beneath it all. The universe changes always. And now, as the final darkness settles gently around you, you let the immense scale of it all drift farther away. The galaxies become distant embers. The black holes fall silent. Even time itself seems to slow into softness. You no longer need to hold the whole universe in your mind. You only need this quiet moment, this breath, this fading warmth. And out there, somewhere far beyond imagination, The stars continue their ancient journey through the night. End of script. Sweet dreams.